Okay, welcome. This is the first of a series of short lectures in mechanistic systems biology. It'll be like 10, 15, 20 minutes each. This is the first one. It's going to be on chemical kinetics. By the way, there's a background noise, which is the air conditioner, because it's a bit hot today in Seattle, so excuse that. So what I've got here are two common reactions you may have seen in your chemistry class. Hydrogen plus iodine gives hydrogen iodide. Let's do this a little tidier. And then the other one, you've got hydrogen plus oxygen gives water. Okay, so the two common reactions you may have come across. Notice that I use different symbols here. One is reversible and the other is pretty much irreversible. You're not likely to find water spontaneously turning into hydrogen and oxygen. So the only way to do that is to push the equilibrium to the left by using something like electrolysis. But the top one, this one here, is actually pretty reversible. It goes back and forth. This is typical for a lot of reactions. You may have come across also maybe in your biology class, you may have come across this one. It's more biologically relevant. 1 glucose plus 6 oxygens gives 6 waters plus 6 CO2s. Okay, this is of course respiration. So what we're going to talk about is the kinetics of these and how you describe these kinds of processes. Let's first start with I'm gonna make it pretty generic. Okay, so I'm gonna use just symbols like A to represent a species. Then I'm gonna put an arrow and then another letter B. And basically, what this means is that some species A is getting transformed into some species B. Okay, and I may have more elaborate ones like A plus B goes to C. All right, so this is a combination of bimolecular reaction. A combines with B to form C, and so on. So okay, so I'm going to talk about reactions in that form rather than have talk about specific ones like those three above. So one thing to bear in mind is that when you start a reaction, of course, in this case, let's say A might get used up as the reaction proceeds, and then in the process I form B. So if I were to plot, for example, concentration of A, let's put a different color for B, concentration of A and B versus, it's usually versus time. Okay, let's say I started off with a whole load of A, right? Of course, I assume I have no B at all. So if I were to do the experiment, I would go to measure A and B over time. I would probably see something, like this. Okay, it will slowly decline as it goes used up, and then B would slowly get made. Okay, we'd see something like that. And what we would do is we then join the dots up, form these lines. Okay, and these show us the progress of the reaction as time goes on. Now, at any particular point, I can take any particular point or any particular time, and I can actually measure the slope here, which will be the rate of reaction. Sorry, the rate of change. Okay. So this thing here is called the rate of change. Okay. So this is quite an important thing to be aware of. So that's the first thing we would introduce, which is the rate of change. Let me write it down here again. Rate of change. Okay, and that usually is a symbol. If I have the species X, I will indicate that with the rate of change symbol like that. Okay, and the units will generally be something like moles per volume per time, right? Moles per liter per second, whatever that be. Now, when I measure the rate of change, of course, I can either measure it by measuring, by watching A, or I can measure it by watching B, or I could even measure it by watching both of them, observing both of them, and seeing what happens to them. Now you'll notice that if I measure A, you'll notice the slope here is negative. So dA by dt is negative. You'll notice that the slope for B is positive, so that B is actually greater than 0. So you notice immediately that depending on which one I measure, I get a different number. One will be negative, one will be positive. Now in this case also, the actual numbers, the absolute values of the numbers will be the same. So remember the symbol for absolute is something like that. So the absolute value for A, dA by dt, is actually the same as the absolute value for B. Okay. The signs, if I were to look at them, if I didn't look at the absolute values, the dA by dt will be negative and dB by dt is positive. The fact that they're the same and the signs are different also means, just out of interest, that dA by dt plus dB by dt equals 0. Okay, so that just tells me that the total mass of the system isn't changing. So for every A that disappears, one B reappears. Okay, so I don't lose any total mass of the system. Anyway, so that's the rate of change. Now, how about this reaction here? So 2A goes to B. Okay, in this case, I would measure dA, I would measure the A, and I would measure the B. Okay. Now, in this case, A is disappearing twice as fast as B, because for every molecule for every B that appears, right, for every B that appears, 2 A's disappear. So the absolute values are definitely not the same in this case. Okay, they're not the same. The signs are opposite again as before, so the dA by dt will always be negative and dB by dt will be positive. Their absolute values are not the same, right? Because for every B that appears, 2 A's disappear. So we can get actually quantitatively different rates of change depending on which species we measure. And in the published work, rather than talking about rates of change, people often talk about instead about the rate of reaction. Okay, the rate of reaction. This is given the symbol V, right? The rate of reaction of velocity V, and it has the same units as the rate of change. Something like that. Lost that for a second. Okay. Now, what's so special about the rate of reaction? Well, the rate of reaction is special because it'll be the same. It's the same number, same sign number, whether I measure A or B. How do I get that to be the case? Well, what I do is I normalize the rate of change with the stoichiometry. Okay, so the stoichiometry is 2 here. There's an invisible one. There's one there. If I normalize with the stoichiometries, I'll actually get a rate of change that is independent of the thing I used to measure it. And the relationship then I want to talk about is this one. So the reaction rate is, so the reaction rate, if I use the species X to measure the reaction rate, then the reaction rate is dx by dt multiplied by 1 over this thing here, Cx, which I'm going to call the stoichiometric coefficient. Okay. Now the stoichiometric coefficient is taken directly from the stoichiometries in front of the species. In fact, these numbers themselves, I often refer to them as the stoichiometric amounts. Okay. So the stoichiometric coefficients are actually the stoichiometric amounts, but the sign is set depending on whether the reactant, whether the species is a reactant or product. So for reactants, the stoichiometric coefficient is short, the coefficient is always less than 0. It's always negative. Okay, and for product, the stoichiometric coefficient is always greater than 0. It's always positive. Okay, but I'd rather, instead of doing that, we'll just say they're either positive or negative. Okay, so if I were to take this reaction here, 2A goes to B, the stoichiometric coefficient for A is -2. Let me do that better. Is -2, and the stoichiometric coefficient for B is +1. All right. Let's do a couple more examples. What happens if I had this probably impossible reaction? 3. So 2a plus 3b goes to 6c, right? Something ridiculous like that. Then the stoichiometric coefficient for A is -2. The stoichiometric coefficient for B is -3. And the stoichiometric coefficient for C, because it's now a product, is +6. Okay, so those are the CX numbers you find here, right? So if I were to measure, let's take that simple example, 2a goes to b, okay, and then the researcher, they measured A, and they got a number for A, dA by dt, but they also measured b. They were able to measure changes in b, they measured that as dB by dt. The reaction velocity in terms of dA by dt is 1 over, what's the stoichiometric coefficient? It's 2, and it's reactant, so I have a minus in front of it, so it's -2. And the reaction rate, you can also get the reaction rate by measuring B, dB by dt, so dt, that's 1 over, now we've got this basically invisible 1 in front of there, and it's a product, so it's plus 1, okay? These two numbers are the same. They're the same, okay? So dA dt over 1 minus 2 is the same as dB by dt 1 over plus 1. And so it doesn't matter now whether I measure A or B, I'll always get the same reaction rate. And this is a convenient thing then to publish in your papers. You talk about reaction rates rather than rates of change, because now nobody cares what you actually use to measure it against, because you've normalized it with respect to the stoichiometry. Might be worth writing it out in this way. Let's rearrange it. So I get dA by dt equals minus 2v, and dB by dt equals plus 1v. So you notice immediately that dA by dt is twice the rate of dB by dt. That makes sense. A is disappearing at twice the rate of B as B is appearing. Because that makes sense, because for every B that appears, 2 A's disappear. Right? So generally, we will always talk in terms of reaction rates, although when it comes to measuring what actually is changing, we then talk about the dx by dt. Okay. So for somebody who wants to build a computer model of this reaction here, what they would do is they would write a differential equation. They would write dA by dt equals, now the stoichiometric coefficient for A is -1, okay? So CA equals -1. And you're arranging this kind of thing here, we end up with -v. Let's write down what the reaction rate is there. So each reaction has a reaction rate, which would donate V. So each of these reactions, these ones up here, that'll have reaction rate, that'll have reaction rate, that'll have reaction rate. And the reaction rate won't matter whether I've measured glucose, oxygen, water, or CO2. It's all normalized by the stoichiometry. So if I go back to this, so I might have a computer model now where I can describe this. This is the model for my reaction. The rate of change of A is equal to -v. Okay, now we haven't said what V actually is. I have said it's moles, per volume per time of some sort. But I haven't told you how we can compute this V, and we'll come to that in the next lecture. But this is basically how you would write down a model for this system, describing how A is changing. I could also write the alternative, which is B. Also do that, and that's plus V. Okay, so the rate of change of B is plus V, the rate of change of A is -V. Okay, I think that'll do it for now.